As promised, we are going to go through the pedigree diagnosis, if you will, in order to figure out which of the likely inheritance patterns that these genes have. Now, we are given a pedigree, as shown here, and we don't know how these traits are passed on to generations. It could be either dominant or recessive, and it could be either autosomal, meaning one of the normal chromosomes, or X-linked, meaning that it is present on the X chromosome. And for us to be able to figure out which is which, the best way for us to do that is to possibly go through each potential scenario and be able to rule out whether or not a potential combination could be viable. Now, what I mean by that is, as you'll see here, we'll scroll down to our first pedigree, and we are going to fill out the genotype for these individuals as though this trait is X-linked dominant. And so when we have a person that has the trait, they would be X big B, so that's just the letter we're going to use for this. If they are recessive, they are going to have X little b. And now remember that if we are talking about an X-linked trait, we also have another chromosome to keep in mind here, which is the Y chromosome that the males will have. And so as we are assigning these genotypes, we can figure out if they are hetero or homozygous in some instances. And it'll be helpful for any time we are looking at an X-linked dominant trait to start with the males, because we know they only have one X chromosome to work with here. And so that'll be easier for us to figure out quickly, are they dominant or recessive? For example, at the top of our page, we have a normal male. And what that would mean in this instance is that they do not have the trait, and so they would end up being X little b Y for their genotype. And now for the mom, we actually don't know if this mom is going to be heterozygous or homozygous. And so what we are going to write, for now at the very least, is X big B, because we know she has the trait, and then a dash, meaning that we don't know what the other chromosome looks like. If we had these two individuals and they got married and had kids, we can now look at the potential genotypes of their children to determine what is potentially going on here. For example, if we are looking at potential offspring, the first daughter over here does have the trait, and so we know that this daughter is going to be X big B, and because we know she is a girl, she's going to have an X from dad, and we know that that has got to be X little b. So this individual is going to be heterozygous. For our son right here, we know that they are going to have the Y chromosome for one, and they are also going to have the trait, which means that they are going to be X big B Y. We can continue on with this, and so if we're looking, the next child is going to be an unaffected male, and because they have they do not have the trait, we can know that they must be X little b Y. So that also means that we now know what mom's other chromosome is, because if she has a son that does not express the trait, that must mean that she has been heterozygous all along. If we continue forward, we have a daughter that does not express the trait, and so their genotype is going to be X little b, X little b. And then finally, we have another affected daughter. And so this daughter is going to have X big B, X little b, because we know that that has to be the case from dad. So now, at this point, we can't necessarily rule out that this trait is X-linked dominant. So we are going to continue on, and we are going to look at the next generation. So if we have this individual, this is going to be our affected male, shown here, and they are married to a normal female, and we know if this is a dominant trait that the genotype for this individual has got to be X little b, X little b. If we are looking at their offspring, we can see that they have a normal male, which would make sense because they have an X little b from mom and then that Y chromosome from dad. So that checks out. But now we run into an issue. We see that this male right here is affected. We know that they have a Y from dad, but the mom doesn't have a big B to donate, because we know that this must have been their genotype were this the case. But that is entirely impossible, because this big B couldn't have come from dad and it couldn't have come from mom. And so at this point, we can say, all right, we don't need to go any farther in this pedigree. We know that whatever this trait is, it can't possibly be X-linked dominant, because we have an individual that would be completely improbable. So let's move on and let's try to see, could this potential trait be X-linked recessive? Which in this instance would mean that if you have the trait, you are missing the dominant trait. So we'd have this for our affected females. The affected males would all have X little b Y, and the normal males would be X big B Y. And the normal females could be homo or heterozygous. So they would be either X big B, X little b, or they could potentially be X big B, X big B. So now we can honestly look through this and insert a number of these genotypes without really even thinking about it. For instance, the mom in this first generation now, if she is affected in this instance and it's recessive, we know that she must be X little b, X little b. We also know that a normal male is going to be X big B, Y. Now, what this means is that all of their offspring who are males should have the trait. If we go through, first up we see an affected female, and that doesn't make sense because we know that dad has an X big B to give that daughter, and the mom has an X little b to give. But if this is recessive, the genotype of this daughter would have to be little b, little b. So actually, right out of the gate, we can see, we know that this trait cannot possibly be X-linked recessive. The same would be true over here for this child in the center. We know that their genotype would have to be X big B Y, and that Y would come from dad, but the mom can't give a big B. And so this child is also an impossibility. Same with this daughter over here. And so we were able to very quickly rule out the possibility for this pedigree and in the inheritance pattern to be X-linked recessive. Alrighty, moving right along. Now we are going to investigate the possibility for these traits to be autosomal recessive. And so we are going to be able to label some of these genotypes right out of the gate. We know that if the female is affected, they are going to be little b, little b. A normal female will be big B, and it will have a dash there, meaning that they could be homozygous, they could be heterozygous. For the males, they're going to look the same as the females because now we're removing that possibility for the X-linked traits. And then same thing with our normal males. We're going to have big B and then a dash potentially because we don't actually know if they are going to be homo or heterozygous because this is going to be a recessive trait. And so if we are looking, if it's an affected male or affected female, we can go ahead and put in all of these little b's for the offspring. And what we also know is that if these two individuals have children that are affected or basically carrying this trait, or I should say expressing the trait, we know that although dad does not have the trait himself, he must at least be a carrier because he needs to have a little b to give to his offspring. That would also then mean that this son right here is big B, little b, because it can only get a little b from mom. And this daughter would also be big B, little b. So we've gone through the first two generations and been able to figure out what their genotypes are. And so far, no issues. Now, if we are looking at the marriages, we see that this affected male had married a normal female. Now, at this time, we don't know if that female is going to be big B, little b, or big B, big B. So I'm just going to put a B here and just put a little dash because we don't know just yet. If we go down, we can see that we have an affected male, so that must be little b, little b, and we have an affected daughter. That must be little b, little b. And so if we actually go back up to mom, that means that she must have a little b to donate, and so we now know that she is going to be heterozygous. If we now look at their normal male son, it is going to be a big B because that came from mom, and then the dad only has a little b to donate, and so this son is going to be heterozygous as well. Again, no issues so far. Let's go back up for a second to look at this final male up in that second generation. And what we can see is that they have two kids and neither of their kids have the trait. So that could mean that this male is big B, big B. It also could mean that he is big B, little b. We genuinely don't know, and we probably won't know. So for this, we are going to leave this big B dash as their official genotype. We can then look to see the offspring, and just like the parents, we don't actually know what combination of big B, little b they have, but we do know that they at least have one allele that is dominant. And so we can conclude that they are big B dash. Still, no problems that I'm seeing thus far. Alrighty, if we visit our last generation here, let's look at these two parents. If we see that the kids are both normal, that might lead us to believe that mom here is possibly big B, big B. Now, ultimately, we can't confirm that 100%. Just because they have two children and both of them are normal doesn't necessarily mean that mom is homozygous. But what we do know is that because dad can only give a little b, both of their kids have got to be heterozygous. Over here, we have an instance where we have an affected female and a non-affected male, and we see that one of their kids has the trait, which means that we know this male has got to be heterozygous because they have to be able to have an offspring that is little b, little b. And then the genotype for this offspring has got to be big B, little b, because this mom can only give a little b. So we've almost gone through this entire pedigree and have seen no apparent issues with any of the genotypes and how things are lining up. Last, we got to just go through is this final family over on the right-hand side, right here. And at this point, we don't know what the genotypes are necessarily from mom and dad. What we can say is that we have big B dash, and looking at their children, the only way we would know for sure if the parents were heterozygous would be if we saw an affected offspring, and we don't. And so in theory, the offspring are going to be big B dash and big B dash, and that is a totally fine genotype to report for a pedigree. The thing that we can look at through all of this is that there's no way to rule out whether or not this is an autosomal recessive inherited trait. So what I'm going to say is that possibly this is how this trait is inherited. To know for sure, let's go through the final scenario, which is our autosomal dominant traits. And again, we can fill out our clues over here, knowing that our normal females are going to have to be little b, little b. Our normal males are going to be little b, little b. And then our affected females will be big B dash, and our affected males will be big B dash, because it doesn't matter if they are homozygous or heterozygous, if they have at least one copy of the allele, they are going to be expressing the trait. And so if we go through and we look at our first generation male, they are normal, thus they've got to be little b, little b. We then have a mom, and we don't know if that mom is going to be heterozygous or homozygous for that trait, and so we'll leave her as big B dash for now. As we go through, we see that this daughter over here has our trait. We know it is dominant, and that must have come from mom. The dad only has a recessive trait to donate, and so that genotype is going to be big B, little b. The same is going to be true for this affected son. They've got to be big B, little b, because they can only receive a recessive gene or a recessive allele from dad. Right here, we have a son, and they are not expressing the trait, meaning that it's got to be little b genotype. which also means we can go back now and determine that mom, if this is all true, has got to be big B, little b, because this son is unaffected. We can look at a daughter and say, okay, cool, they are also unaffected, so that's got to be little b, little b. And then over here, we have a big B, little b daughter. Very good. Let's look at the next generation. Starting from the left-hand side, we see that this big B, little b mom, or sorry, dad, marries a homozygous recessive individual because we know that because they are unaffected, and that means that they must be recessive. And we see here first that they have a normal male son, which is possible because they have little b's to get from both parents. And we have an affected son that is going to be big B, little b, because we can only get a little b from mom. And then over here, same thing. We're going to have a heterozygous individual. For the rest of this, we can basically fill in the remainder of these traits because anytime we have a light blue square or circle, we know that they are going to be little b, little b. And this is, in fact, going to be possible thus far if we're looking at how things can be passed down. We see that these two parents here are both recessive, so sure enough, they're going to have kids without the trait, which will be consistent. And we also know that the people that those individuals marry are also going to be little b, so we can plug those in as well. So very good. We have now 3 generations, and again, just like the last time, we don't have any issues with the genotype as it stands now. Continuing on, starting on the left-hand side of the final row, we have 2 individuals that are going to be little b, and that is absolutely possible because our dad, we already know, is heterozygous, and our mom is homozygous recessive, and so sure enough, we can get little b's all around. Down here, we have a big B from mom, little b from dad, and just so happens that these 2 are probably going to be 2 little b's because again, they are recessive. And then over here, this one's very easy. We just have little b's all the way across. And so we've gone through and we've completed the genotypes entirely for the potential of this being an autosomal dominant trait, and we have seen no issues. So what we can conclude is that it's very possible that we have an autosomal dominant trait. All we can really conclude based on these pedigrees is that we know for sure that this is going to be autosomal because we were able to rule out that it can't possibly be X-linked. Now, whether or not this is dominant or recessive, we actually don't know still, and sometimes that'll happen. Now, what I will say is that on an exam, if I made everyone go through this whole process, there would be a correct answer, and I wouldn't leave it quite so ambiguous, but know that just because we have all of these genotypes filled in for our autosomal dominant gene combination, and just because we have some that we have question marks around for this big B dash, as shown here, and then all down here, that doesn't actually mean that we can rule it out or that it's any less likely to be an autosomal recessive trait than it is autosomal dominant. So we can basically conclude that, again, it's autosomal, maybe dominant, maybe recessive, and we just genuinely don't know. Now, if we had a few additional children to look at, we'd maybe be able to conclude which of the dominant or recessive traits it would be. But at this time, this is what we came up with. Hopefully, this helps.